Good morning. Welcome back. Hope you guys had a good spring break. And now it's time to get back to business. So I have a couple of announcements. The first announcement is you're gonna have your second exam this coming Tuesday, so a week from today. The exam is gonna cover the material that we're gonna cover today. And also, if we don't have time to complete the material or the lecture slides of today, the material will be finished on Thursday. So that will also be part of the exam. The exam, you should expect the same format like the first exam. So a first section with true or false questions, and a second section with problems, similar to the ones you have seen in the homework. So one more time, the exam is a week from today, the second exam. I posted one homework that is split in two halves. So if you go to tracks right now, you'll see that you have a homework 5 and homework 6. Homework 5, again, I just split the homework in two, but initially it was just one homework. The first part, which is homework 5, is due on Thursday, and that is going to cover the material on the artificial solutions. So basically the M method and the two-phase method. And the second homework is going to be due, or homework number C is due on the day of the exam. And for that homework, you'll see problems related to the material we're going to finish today, which is sensitivity analysis. So the exam is going to cover up to sensitivity analysis, which is the material that we're going to hopefully finish today. Any questions? Okay, so so the last thing we did in class before spring break was to go over sensitivity analysis. And basically what we're trying to do right now is to decide, or basically find out the changes that you can make to your problem in terms of the resource availability and also in terms of the cost for the product that would not change your optimal solution. So if you found an optimal solution for your problem and you initially had a limited number of resources for each phase of your production, what we're trying to decide right now is how can you change the availability of these resources and still keep the same optimal solution. So we covered the graphical sensitivity analysis already, and we started the discussion on the algebraic sensitivity analysis. Excuse me. Any questions about the graphical sensitivity analysis? We discussed two different types of sensitivity analysis, one for the right-hand side of the constraint and one for the objective function coefficients. So we're going to do the same thing with the algebraic. We're going to start with the right-hand side, and then we're going to transition to the coefficients of the objective function. So we covered this already. I just want you to get an introduction one more time of what we're trying to do. So this section demonstrates the general idea of the sensitivity analysis using algebraic method. The two cases will be considered. The first one is the sensitivity of the optimal solution to changes in the availability of the resources, the right-hand side of the constraints, and the second is the sensitivity of the optimum solution to changing to changes in the unit profit or the unit cost. So this one will be targeting the coefficients of the objective function, which most of the time is the cost of the revenue that you are making by selling or producing a unit of a product. So we use this example for our lecture, the explanation. We will keep using this example. This is a production problem. We have 3 different products. We have the revenues per unit for each one of the products. We have the times per train, and we have the time that it will take to produce each product per station. And we came up with the formulation. So we were trying to maximize the profit, which is right here. So we are doing $3 per product 1, $2 per product 2, and $5 per product 3. And here, these 3 are your products: trucks, trains, and cars. And we have 3 constraints, 1 per operation. And the right-hand side, again, is the number of hours that you have available, or in this case, minutes that you have available for each operation. He asked this question, and one of you was able to tell me how many of each product we were producing based on the optimal solution of the tableau. So this is the optimum based on the optimal tableau. You should be able to find out how many of each products you produce with the optimal. So then we transition to determine the dual prices and the feasibility range for the right-hand side. And what I explained on Thursday was that you can add these 3 variables to the right-hand side of your constraint and use those variables to determine the dual prices. Okay, so that's what we did. We added those 3 variables, 1 per constraint, and then we use simplex tableau to find the values of those coefficients. So to express the optimum simplex tableau of the modified problem in terms of the changes of D1, D2, and D3, we first rewrite the starting tableau using the new right-hand sides, which are listed here: 430 plus D1, 460 plus D2, and 420 plus D3. Those values, those 400 something, were your initial right-hand sides. Those are the values that tells you the availability per operation. We are adding these 3 coefficients, or these 3 variables, to find out the dual prices. So in order to find those values, we create a new initial tableau for the simplex, which essentially is the same thing. So if you look at this side of the table, it's the same thing that you found on the simplex, but now we are adding these 3 columns. Any questions so far? Okay, this is very important. So I want you to make sure that you're following. So the 2 shaded areas are identical. So that's something else that you need to notice here. So these are the variables that you are having as your basic feasible solution. And these are the 3 new variables that are coming after adding those 3 to the right-hand side of your constraints. And both of them are identical. So if we repeat the same simplex tableau iterations, like you know how to do, you know how to operate the simplex algorithm, the columns in the 2 highlighted area will also be identical in the optimal tableau. So if you're not following the lecture using the computer, please turn off your computer or your computer screen. So as you can see now, this is the optimal tableau, and these two areas are the same. So the new optimal tableau provides the following optimal solution. So if you go here, you get the optimal solution. This is your objective function value. And now you have a coefficient for D1 and a coefficient for D2. So your optimal solution will add those two coefficients times the variables. So Z is going to be equal to 1,350 plus D1 plus 2D2. And X2, now you have the value of X2 from here, the first row, 100. But now you need to add those coefficients times the values of the variables to your optimal solution as well. So now you have a value for X2, X3, and X6, but those are not only integer values, you also need to add the coefficients corresponding to the values of D1, D2, and D3. And I believe we stopped here. No, we went step. So this is your optimal solution. One more time. This is the same thing that we had on the previous slide. But the equation shows that a unit change in operation 1, capacity, changes the value of the optimal solution by 1. And you can see that from here. So if you add D, if you change that coefficient is 1. If you change the value of that variable by a unit, that would increase the value of the objective function by 1. If you increase D2 by a unit, that will increase the value of the objective function by 2. And that's because now we have those three new coefficients and those two values added to the objective function. So a unit change in the operation 2 capacity changed the objective function by 2. And a unit change of operation 3 will increase the value of the objective function by 0 because D3 is not part of the objective function. Any questions so far? Okay, so this means that by definition, the corresponding dual prices are 1, 2, and $0 per minute for operations 1, 2, and 3. So one more time, we have the objective function. We are adding these two variables with those coefficients to the objective function. And those coefficients are telling you if you increase this capacity or the capacity of this resource by 1 unit, I will increase the objective function by the coefficient of that capacity. Okay, so now we need to find out what are the ranges that we can use to increase and decrease these values in order to keep the optimal solution the same. So that's what we call the feasibility rate. So the current solution remains feasible if all the basic variables remain non-negative. So we have our basic variables, x2, x3, and x6. So your basic variables are coming from here, x2, x3, and x6. So in order for the current solutions to remain feasible, they need to be greater or equal to 0 or non-negative. That means that x2 equal to 100 plus 1/2 d1 minus 1/4 d2. This is coming from here. x2 equals this. In order for that to be Non-negative, we know that needs to be greater or equal to 0. X3, same thing, equals 230 plus 1/2 D2. And for that to remain positive or non-negative, that needs to be greater or equal to 0. And finally, we have X6, which equals 20 minus 2 D1 plus D2 plus D3. That needs to be greater or equal to 0. So again, we already know the dual price. We know that if we increase this resource by this many units, that will increase my objective function. I will make more money. And I want to be able to increase those resources as much as possible so I can make more money. But what happened? If I increase these values over the feasibility range, the optimal solution will change. So I need to make sure that I know what are the ranges so I can increase these resources as much as possible so I keep the same optimal solution. Okay? And as optimal, we know that that is the best solution that we're going to find. Okay, so simultaneous change D1, D2, and D3 that satisfy these inequalities will keep the solution feasible. The new optimal solution can be found by substituting out the values of D1, D2, and D3. So I have an example next. Suppose that the manufacturing time available for operations 1, 2, and 3 are 480, 440, and 400 minutes. Then we can find the values of D1. So D1 is going to be 480 minus 430, that's 50. D2 is going to be equal to 440 minus 460, that's minus 20. And D3 is going to be equal to 400 minus 420, that's minus 20. Those are the original values. So these are coming from the example. These are given. And the other ones are coming from the original values. So now I'm changing those. I'm telling you, instead of the original values, this is what you have. So those are the differences. Then we can substitute these D values in the feasibility conditions, and we get the following. X2 is going to be equal to 100 plus 1/2 times 50 minus 1/4 times minus 20, and that's going to be equal to 130. Is that positive? Is that value positive? 130 is positive, is greater than 0. So this is greater than 0. So this is feasible. This is feasible. Then let's check X2. I'm sorry, X3. X3 equals 230 plus 1/2 times minus 20. That's equal to 220. That's greater than 0, so it is feasible. Now let's check X6. This is 20 minus 2 times 50 plus minus 20 plus minus 10. and that is equal to 110, but that's negative. So that's less than 0, and that is infeasible. So remember, what we're trying to see is if you are satisfying the conditions. These conditions means that you need to be greater than or equal to 0 in order for the solution to be feasible. x2 and x3, when you substitute d1 and d2 and d3, gets you positive values, but when you substitute on x6, that gives you a value that is less than 0. So that is infeasible. So the calculations show that over there. So what the calculations are showing is if you increase those capacities by those amounts or decrease the capacity by those amounts, your solution is no longer the same, it's not feasible. So that's why you need to find out what are the ranges that you can use to increase and decrease your capacities. Okay, because if you do it without taking into account those feasibility rates, then you might end up having an infeasible solution. So let's look at a different example. So we went from 480, 440, and 400 minutes. Now we're going to test another X scenario. Now we have these numbers, 400 for operation 1, 448, and 430. So if we proceed as we did for the first case, these are the values for D1, D2, and D3. If we substitute those numbers into the feasibility conditions, we get x2 equals 100 plus 1/2 times minus 30 minus 1/4 times minus 12. That equals 88, and that's greater than 0, which means that that is feasible. We have x3, 230 plus 1/2 times minus 12. That equals 224. That's greater than 0, and that's feasible because it's positive. And then x6 equals 20 minus 2 times minus 30 plus minus 12 plus 10. That equals 78. That's greater than 0, which means that it is also feasible. So the new optimal feasible solution is x1 equals 88, x3 equals 224, and x6 equals 78, with an objective function of 1286. Any questions? So if you go back to the graphical solution, you remember when we were dealing with the capacities, that means that you were moving the constraint from left to right, and when you move it to the right, then that optimal solution will move with that constraint. So that's what's happening here. So you're moving that constraint, and the optimal solution is moving with the constraint. Okay. The given conditions can produce the individual feasibility range associated with changing the resources one at a time. For example, a change in operation 1 time only means that D2 and D3 will be equal to 0. So if you only change the first operation and you keep the other ones the same, then you can assign a value of 0 to D2 and D3 and then focus only on D1. And that's what this is saying. So the simultaneous conditions thus reduce these feasibility conditions to the following. So we have x2 equals 100 plus 1/2 d1. We have x3 equals 230 and x6 equals 20 minus 2 d1. And again, this is because we are saying that d1 is the only one that is going to change, and d2 and d3 equals 0. So this will become 0, this will become 0, and these two will become 0. So that's how you get these three expressions. So we are looking at the conditions only for D1. So in order for D to be greater than 0, D1 needs to be greater or equal to minus 200. And that's by solving for D1. For this one, this will always be greater than 0 because it doesn't change, has no variables, so it's a fixed amount. And x6, for this to be greater or equal to 0, then D1 needs to be less than or equal to 10. And you have found the feasibility range for D1. So that means that D1 must be between 10 and minus 200. So if you change D1, if you increase or decrease D1 within those range, then you will keep a feasible solution. So this means that the dual price for operation 1 is valid in the feasibility range minus 200 D1 minus less than or equal to 10. So again, we found the dual price for D1 was 1. So an increase of a unit for operation 1 will increase the optimal solution by 1 unit. So if you increase by 100 units, then that means that you're going to make $100 more. But what happened? You can only increase that up to this number. So if you go up to 10, you increase the capacity of operation 1 by 10 units, then you will make $10 more. But if you go over, so if you go to 11, you increase the capacity by 11 units, that solution would not be feasible. So the more that you can increase this operation is 10 units. That's what this range is telling you. And that's only for operation 1. We can perform the same analysis for D2 and D3. What I'm saying is, instead of, if you're doing this process for D2, then you're going to assign D1 a value of 0 and D3 a value of 0. And you're going to get the same, well not the same, but the same variables. But instead of having the coefficients for D1, you're going to have the coefficients for D2. You can solve for D2 and get the range for D2. Then you can perform the same operations for D3. You're going to assign D1 equals 0, D2 equals 0, and then find the variables for D3 with the coefficients for D3, perform the same operation, solve for D3, and get the range for D3. So you can perform these two extra operations on your own, following the same steps, but what you're gonna get, you can show in a similar manner that the feasibility range for operations 2 or 3 are these two, because that's what you're gonna find. And we can summarize the dual prices and their feasibility range for the cycle model as follows. So we're gonna have the dual prices, right? You're looking at the operations. One more time, you're looking at the sensitivity of adding extra capacity to your process. So how would that affect your optimal solution? So we have three operations, and if we increase the capacity of operation 1 by 1 minute, how would that affect my optimal solution? How much money would I make? So what the dual price is telling you is, if you increase this operation by 1 unit, you're gonna make an extra $1. If you increase operation 2 by 1 unit, you're gonna make $2 more. If you increase operation 3 by 1 unit, you don't make any money. So that doesn't make any difference. But now, if you find the feasibility range, this is telling you how far can you go by increasing this capacity. So we found that the feasibility range, you can increase D1 by 10 minutes and you will make $10 extra, but you cannot go over 10 because that will make your solution infeasible. For operation 2, you can increase that operation, the capacity by 400 units. And you will keep the same feasible solution, same optimal solution. But if you go over 400, then you will get an infeasible solution. Same thing applies for decreasing. You can increase or decrease, but this is your range. Finally, operation 3, you can increase this, doesn't make any difference because you're making no money. Okay, so you can make that as big as possible. And that will not change your optimum, but the minimum that you can assume is this one. So, if you go back here, so in terms of a resource amount, your current values are here. You have 430 minutes, 440 minutes, and 420. If you increase this capacity by 10, that means that your maximum is going to be 440. If you increase this one by 400, your maximum is going to be 400. That should be 420. This is the value that is wrong. The original is 460. So, okay, yeah. So if you increase this by 400, that makes 460. And if you increase this by infinite, that will make that number infinite. Okay? So this table is very important. It's important that you understand what these numbers mean. Because I can ask you questions in the exam about, I can give you a table and ask you, for example, if you increase the capacity of operation 1 to 20 by 20 units, would that give you a feasible solution? The answer is no, because the maximum that you can increase the capacity of operation 1 is 10. Okay? So go back, review what this means. Again, dual price, a unit of capacity that you add to operation 1 will increase your revenue, the objective function by 1. This will increase that by 2. So on. Any questions so far? Okay. Now let's talk about, so we talk about the dual price, now let's talk about the reduced cost. So in the historical model, the objective, or the Z equation in the optimal tableau, can be written as this. So we have the optimal solution, 1,350. This is the objective function value. And then you also have some coefficients here. So we can use those coefficients to write the objective function in this based on the optimal tableau. So we have the coefficient for x1, coefficient for x4, coefficient for x5. For these guys, that doesn't matter because that's 0. And we are not taking into account these yet. So we can rewrite this in this way. So the optimal solution does not produce toy trains. And that's why we get, for x3, we get a value of 0. Remember, x3 was for trains. So in your optimal solution, you get, it's x1. So in your optimal solution, you don't get a value for x1, but you get x2 equals 100, x3 equals 210. The reason can be seen from the z equation, where a unit increase in x1 decrease z by 4. So if you go here, and if you look at this optimal objective function, if you increase the value of x1, which is the trains, that would decrease your objective function by 4. So that's why you end up producing no trains. We can think of the coefficient in the z equation as a unit cost because it costs a reduction in the revenue. So this value here, this guy here represents the trains. And in the optimal solution tableau, we found that that variable is with a coefficient that is negative, which is -4. And if we increase the value of x1, that will decrease the value of the objective function by -4. So that means that if you produce a unit of trains, you will decrease your objective function, or you will make less than what you will get by not producing those units. Does that make sense? Okay, we are going back to the optimal tableau. This is the optimal tableau. You know that the objective function is represented in row 0. The optimal solution is here. This is, you are making $1,350. But that objective function is also, you can represent that objective function also with the coefficients of that 0. So if you have x1 here, if you look at x1, which represents the number of units that you can produce for trains, that coefficient is -4. Any unit that you produce of train will make you reduce your profit by $4. So to facilitate the explanation of the objective function sensitivity analysis, we first we need to define the reduced cost. So a reduced cost per unit equals the cost of consumed resource per unit minus the revenue per unit. Okay, so the reduced cost per unit is equal to the cost of a consumed resource per unit minus the revenue per unit. So to appreciate the significance of this definition, in the original TOEIC model, the revenue per unit for toy trucks is $2, is less than for toy trains. So that's something that you saw in the original formulation. So even though you're making less money with the trucks, you end up producing more trucks and producing no trains, because it costs you more to produce those trains than what it costs you to produce a truck. Yet the optimal solution producing toy trucks, x2 equals 100 units, and no toy trains. The reason is that cost of the resource used by one toy truck is smaller than its unit price. So we can see that an unprofitable variable, such as x1, which represents the trains, can be made profitable in two ways. One, by increasing the unit revenue. So if instead of making $3, we increase that to $5, that will make the unit maybe producing those trains more appealing to the problem, and we may end up producing those toys, or by decreasing the unit cost of consumed resources. So those two areas kind of make sense. You increase your revenue or you decrease your cost. In most situations, the price per unit is dictated by market conditions and will be very difficult to increase at will. So you don't want to sell a computer or a tablet for $1,000 when the market price is $500. You will not be able to sell it. So that's what that means. So we need to find those optimality range, as we did for the right hand side. So first thing we saw in this class today was how changing that the right hand side of the constraint, the number of units that you have available for each operation, how would that affect your optimal solution? Now we are looking at the second case, which is basically how changing the price of the product affect your optimal solution. And that so that development is based on the definition of the reduced cost. So in the Toyco model, let D1, D2, and D3 represent the change in unit revenue for toy trucks, trains, and cars. Then the objective function becomes the following. We have the maximization of the objective function equals 3 plus D1 x1 plus 2 plus 2D2 x2 plus 5D3 plus D3 x3. We first considered the general situation in which all the objective coefficients are changed simultaneously. So we're going to change all of them at the same time. With the simultaneous changes, the zero in the starting tableau appears as follows. So this is how your initial tableau will look like. Okay, so we're going to put that new zero into the initial tableau, and we're going to find the solution using the simplex method, but having this as your initial row. So when we generate the simplest tableau, the optimal iteration will appear as follows. So this is how the optimal solution will look like. Now you're going to have your solution in the zero using coefficients D1, D2, and D3. So for x1, you have this expression. For x4, you have this expression. For x5, you have this expression. And your optimal solution is here. As you can see, this becomes very hard to do manually. So I would not ask you to create or to build something like this in the Excel. However, you need to understand what is important behind it. So again, I'll go back to understanding what the dual price means, what the reduced cost means, and so on. With that being said, you get that zero by performing the simplex method, and you still have the same solution. You get x2, x3, and x6, and you have 100 and 230 here as your values for x1, for x2 and x3. The new optimal tableau is the same as in the original optimal tableau, except for the reduced cost. This means that changes in the objective function coefficients can affect the optimality of the problem only. Okay? So, you really do not need to carry out the simplex row of iterations to compute the new reduced cost. An examination of the new zero shows that the coefficients are taken directly from the constraint coefficients of the optimal tableau. So a convenient way for computing the new reduced cost is to add a new top row, like the one I have here. So you can add that row to the optimal tableau. A new leftmost column, this one. So we have D2 and D3 because they are corresponding to the decision variables that are in the optimal solution. So D1 does not show up here because X1 is not part of the optimal solution. So we're going to add that extra row at the top and that extra column to the left of the tableau. And for the leftmost column, the top element is 1 in the 0, followed by the change di for the basic variable x1. So that's what I just mentioned. Keep in mind that if di is equal to 0 for slack variable x5, so for a slack variable like this one, you have no d values. And to compute the new reduced cost for any variable, multiply the element of its column by the corresponding elements in the leftmost column and add them up and subtract the top row element from the sum. So we're going to use these coefficients. So we're going to multiply 1, 4 times 1, minus 1, 4 times d2, and 3 over 2 times d3. So this is how this look like. So we're going to have 4 minus 1/4 times d2. So that's this one times this one times plus 3/2 times d3. So this is a multiplication sign. And this is also multiplication. And that's going to be for D1. So again, we'll have the following. We have 4 for x1, we have 4 times 1 plus minus 1/4 times d2 plus 3 over 2 times d3 plus 2 times 0, and then all that minus D1, which is here. And if we solve this, we get 4 minus 1 over 2 D2 plus 3 over 2 D3 minus D1. So instead of solving the tableau with the coefficients from star, you can solve the simplex, you can solve the problem using the simplex algorithm, as you know, and then you can find those reduced costs by adding this column and that row, by following this procedure. The current solution remains optimal so long as the new reduced costs or C equation coefficients remain non-negative for the maximization case. We thus have the following simultaneous optimal conditions for corresponding to non-basic x1, x2, x4, and x5. So I'm sorry, this is x4, x5. So we have 4 minus 1, 4 d2 should be 2, sorry, d2 plus 3 half d3 minus d1, and this needs to be greater or equal to 0. We have 1 plus 1 half d2, and this needs to be greater or equal to 0, and we have 2 minus 1 4 d2 plus 1 half d3, and needs to be greater or equal to 0 to remain optimal. So this corresponds to x1, which is the same as we did here. This one corresponds to x4. The reason we are doing x4 is also a snack. So we have x4 and we have x5. Yes, sir.
Why does it change from negative 1 or D2 to
Where's this one, sir?
yeah,
That's 1 half.
right, but 1 4
Oh, yeah. So I guess this one is a little bit incorrect. It should be 1 4 for both. Sorry. Yeah. I was just, since I knew that they were the same, I was using the same coefficients. Yeah. Sorry about that. Yes, that was a typo. Any other questions? So the optimality conditions, as long as this is satisfied, we will keep our feasible solution and we'll get an optimal solution. Okay. Remember that the reduced cost for a basic variable is always 0, as the modified optimal tableau shows. For example, suppose that the objective function of Doikos is changed from this to this. So this is the original one, and we are changing the prices, and yes, the price of selling those units. For trains it was $3, now it's $2. For truck it's $2, was $2, now it's 1, and for the last product goes from 5 to 6. Then D1 is going to be equal to 2 minus 1. D2 equals 1 minus 2. And D3 equals 6 minus 5. And this should be 2 minus Let me check something really quick. So this goes from here to here. This is 1 minus 2, and this is 2 minus 1. This should be 2 minus 3 here, and this should be minus 1. Again, we are looking at differences here to here, 6 minus 5, 1 minus 2, and 2 minus 3. That should be minus 1. Substitution in the given conditions yields the following. So, write that down here. We get 4 minus 1/4 times minus 1 plus 3/2 times 1 minus 1 times minus 1. And that is equal to 6.75, which is greater than 0. Satisfied equals feasible. Then we have 1 plus 1 over 2 times minus 1. That's going to equal to 0.5, and that's greater than 0. That's feasible. And then we have 2 minus 1/4 times minus 1 plus 1/2 times 1 equals 2.75. That is greater than 0, and is also feasible. So you can change the coefficients of the objective function in such a way you can check the optimality conditions, and that's telling you that you will keep a feasible solution. The optimal solution will be the same. And that's what we state on the next slide. Just let me know when we can move to the next one. Are we good? So the results show that the proposed change will give the current optimal solution with the new value of z equals to this. The preceding discussion has dealt with the maximization case. The only difference in the minimization case is that the reduced cost or the equation coefficients must be less than or equal to 0 to maintain optimality. So instead of looking at greater or equal to 0, we are looking at less than or equal to 0. Now, I want you to see how this sensitivity analysis is done using Excel, the solver in Excel. So let me know when you're done so I can move to the next thing to show you that. So I have programmed this same example that we discussed in class using Excel, and I will make it available after the class. So if you want to take a look, it will be available on tracks. And what I'm going to do right now is explain on these couple of slides here. So I'm just going to show you with the computer. So here is the TOEICO model. So we have our objective function coefficients. We have the coefficients for the constraints. So operation 1, operation 2, and operation 3. These are the coefficients. These are the coefficients for the objective function. We have the right-hand side. And the solution is here. So the optimal solution, again, is to produce no trains and 100 trucks and 230 cars. And this is the objective function value. If you want to generate the sensitivity analysis report in Excel, you go to Solver. Here you're going to have your model. So when you solve your model, this is the screen that you'll see. Excel also allows you or asks you to, if you want to generate any extra reports, if you click on this one, it will generate the report for the sensitivity. So if you click there and then you click OK, you'll still have your optimal solution here, but if you go here to the tabs, you'll see the sensitivity report. So if you click on that report, you'll see these two tables. So here you can see that we have the variable cells and the constraints. For the constraints, remember the dual price. You can also name the dual price, or you can call it dual price, the child price. So the child price is the same as the dual price. So if you remember for operation 1 unit, if you increase that by 1 unit, it will increase the objective function by 1 unit. If you increase operation 2 by 2 units, it will increase your optimal solution by 2 units. You also have the allowable increase and allowable decrease. So using these values, your right-hand side, your allowable increase and your allowable decrease, you can create or generate your feasibility rate. So what you're going to do is, the upper bound is this plus this, 140, and your lower bound is this minus this. One more time, your upper bound is this plus this, lower bound is minus this. So this is for the dual price, and this is for the reduced cost. So the reduced cost is here. Remember when I mentioned that adding a unit of X1 or trains will reduce your optimal solution by -4, meaning that it will cost you to produce a train. So that's why -4 is here. That's for X1. So producing an extra train will cost you -4. So that's why you end up having no trains produced. For the other two, the reduced cost is 0. So that's why you end up having a production for the other two. I would recommend you to go look at this table, which is also in your slides, and try to match what we discussed in class with what you are seeing in this table. In the exam, I can provide you with a table like this, and then you can answer questions based on the table. Okay? So, any questions? Yes, sir.
So the upper bound for this bottom table, the third row, is the 420, right? The upper bound is 420.
The upper bound will be infinite.
Oh,
Yeah, because this is a large, very large number. So 1 to the power of 10. So it's a very large number. And the lower bound will be 400. Yes, 400. Any other questions? Okay, so I'll see you on Thursday. Remember that you have homework.